So next we're going to talk about how energy relates, so potential and kinetic energy specifically, for how it applies to chemistry. So potential energy, which we'll often abbreviate PE, it's stored energy. So it generally, very broadly speaking, it results from position or composition. Now, in terms of chemistry, what we mean, it's usually the energy that is in chemical bonds. To say energy stored within chemical bonds is kind of the incorrect way to say it, but that's what most people think. But there's energy associated with chemical bonds. So when two atoms come together, energy is released, and then it's gonna, sorry, I should draw my little arrow this way, but energy is released, and then it's gonna require energy to break that chemical bond. So there's potential energy in that bond. Kinetic energy, which we'll usually abbreviate KE, it's the energy matter has as a result of its motion. So in terms of chemistry, we're specifically talking about temperature or thermal energy. Now, temperature and thermal energy are not strictly speaking the same thing, but that's what we're talking about. Particles are always moving. That's one theory or one aspect of kinetic molecular theory, which we'll get into later. But particles are always moving, and that motion is related to their kinetic energy. So, and then temperature and kinetic energy are also proportional. Energy can be converted between the two types. So we could have potential energy convert to kinetic and vice versa. So a real world, like physical example, a boulder at the top of the mountain has potential energy. So it has, we might say like it has the potential to roll down the hill. If you push it down the mountain, potential energy is converted into kinetic. So, here's our mountain, here's the boulder at the top of the hill. It has potential energy down here. It has the potential to roll down the hill. As it rolls down, it starts to pick up speed. So it's motion. Basically, it's starting to get in motion, and it gets faster and faster and faster. So the potential energy is being converted into kinetic. But that's the idea, is we can have energy conversion, and it's the same thing in chemistry. We can have energy being released when we have two atoms come together, when we form a new molecule, or it could be a new compound. When we form new bonds, energy is released, and that energy, it was potential, it could turn into kinetic, so it could increase the temperature of the surroundings, for example. Another example, talking about a cannonball. So when the cannonball is still in the cannon, it's not moving, it's just at rest, and then we fire the cannon, and then as it gets to the very top of its flight, we say the kinetic energy is at a minimum, because actually when you have something that you throw it up in the air, it's kind of slowest. It's still moving in the forward direction, but it rises up and then it falls back down. So its motion is at a minimum, so its kinetic energy is at a minimum. And then the potential energy is at a maximum because it's as high off the ground as it possibly can be. This is more like a physics example, but it's the same kind of thing. Kinetic energy, potential energy can be applied to chemistry just the same way as it can be applied to physics. Now, in terms of kinetic energy and temperature, all substances are going to have kinetic energy regardless of their physical state. It's just a matter of how much. Do they have a lot or little? Now, one reason for this is because maybe you've heard of absolute zero. And absolute zero is usually referring to 0 Kelvin, so I'm using the capital K for Kelvin. But absolute zero, 0 Kelvin, Kelvin is a type of way of measuring temperature, just like we have Celsius and Fahrenheit. Absolute zero is when the substance, the particles, are no longer moving, so all motion has stopped. And it's only theoretical. It's not actually possible to get something all the way down to absolute zero. So everything in the universe has a temperature that's above absolute zero, and therefore all substances have some kinetic energy. If they're extremely cold, they have less. If they're warm, hot, they have more kinetic energy. Solids have the lowest kinetic energy, and gases have the greatest. And generally, as you increase the temperature of a substance, you're also increasing the kinetic energy. So kinetic energy and temperature are proportional, and this little squiggly is kind of saying they're proportional. That means is proportional. So kinetic energy and temperature are proportional to each other. As we increase the temperature of a substance, we also increase the kinetic energy of that substance. And this table kind of summarizes what we just said. So solids have low kinetic energy relative to the other states of matter, and their movement is negligible. So on a molecular level, if you could zoom all the way in and look at the individual molecules, they won't be moving around quite as much compared to like a gas, for example. Gases have very high kinetic energy, so the particles are flying around, buzzing about each other very, very fast. Unrestricted movement, because if remember, gases occupy the volume of their container, so the particles will spread out as far as they can possibly go. With liquids, it's also high kinetic energy, and we say restricted only because if you've got like a beaker of water, the water's kind of trapped at the bottom of the beaker. The water's not going to just jump up here sometimes and then jump back down. The water is always going to be at the bottom. So that's why we kind of say restricted. And also the particles, they are attracted to each other. So later we're going to learn about something called intermolecular forces. And liquids especially, solids as well, and gases to a small extent, but liquids in particular feel what we call intermolecular forces. And that also restricts their motion. So just like matter, energy cannot be created or destroyed, but it can be converted from one form to another. So we talked about that. It can go from potential to kinetic, and it can go from kinetic to potential. And this is called the law of conservation of energy. So we have law of conservation of mass, and we have law of conservation of energy. And there's primarily 6 forms of energy: heat, light, chemical, electrical, mechanical, nuclear. And I say primarily because maybe you're talking to somebody who's studying physics and they might say sound energy, but then you can say, well, isn't sound energy kind of like mechanical energy? And you'd be like, yeah, it is. So primarily 6 forms, but we're just going to be working with the energy in bonds, so that's like chemical energy, and then heat, which is essentially thermal energy or kinetic energy. These other forms of energy, like light energy, so when you have a packet of light called a photon, that has energy with it. Electrical energy we'll be getting into later when we talk about oxidation reduction reactions in this class. And then nuclear energy, that's the energy that's actually within atoms. So we haven't talked about atoms quite yet, but we will. There's energy associated with the inside of an atom. So the protons and neutrons being together, that's what we call nuclear energy. But this is not for this video, but it is for this week. So then, regards to changes, whenever we do a chemical change, energy is going to be transformed. So for example, in this one, water plus electrical energy, we get hydrogen, oxygen, gas. So energy is required in this example. We have to put in electrical energy in order to convert the water into hydrogen, oxygen, gas. So energy is being absorbed in this example because energy is on the reactant side. So when we have an arrow, let me just erase a little bit. So this arrow that's right here, that's showing a chemical reaction. So we usually write reactants on the left side and then an arrow and then products on the right side. So we've got water as our reactants and then hydrogen and oxygen as our products. Energy had to go in for that chemical process. And then the reverse, if we have hydrogen gas and oxygen gas and maybe give it a little spark, kind of like we're trying to start a fire, energy is ultimately released and we get water and a bunch of heat energy. So most people are familiar with fire and fireworks and any sort of combustion, firing up the grill in your backyard. You get heat out of that. So some chemical reactions require energy and energy has to be absorbed, and some chemical reactions release energy, and we have a special term for that. So absorbed, when energy is absorbed, we call it an endothermic reaction, and when energy is released, we call it an exothermic reaction. Exo kind of like the energy is going out, endo is kind of like the energy is going in. But law of conservation of energy basically says that the amount of energy absorbed equals the energy released. So energy, we've had to put energy in for this process, and where did that energy go? it went into the chemical bonds. And then here we had energy coming out from the chemical bonds, and that showed up as heat energy on the other side. So this heat energy is your kinetic energy, and the energy that we got out of the bonds, that would be potential energy. So again, you have potential being converted into kinetic. Energy is not lost. So then combining the two, so everyone has seen this equation, probably most famous equation in science, E equals mc squared. But what this equation really means is that energy and matter, mass, so lowercase m, are related. C is the speed of light. So the numerical quantity that relates the two. But ultimately what it's saying is that mass and energy actually can be interchanged, and this happens inside stars all the time. If you were to actually take up or like count up the mass of some hydrogen atoms or hydrogen nuclei before and after they did their nuclear reaction in the star, you would find that there's a difference in mass, and that mass comes out as energy. But the E equals mc squared is basically saying that mass and energy are related. And this is what Einstein was famous for, but he was famous for a handful of things. And then we can call this the law of conservation of mass and energy, but it's basically saying that the total mass and energy of the entire universe is constant. Now, we're not going to be worrying about this relation with this class. We're going to focus on either just mass is conserved or energy is conserved, because we're not doing nuclear reactions when on a fundamental chemistry level. Even on higher level chemistry classes and labs, we're not doing nuclear chemistry. So just focus on law of conservation of mass, the mass of the reactants equals the mass of the products, and then law of conservation of energy, where energy is not lost, it just changes into different forms, and maybe you can't see it, maybe you have to think about what did that energy turn into, but energy is conserved.